Hi all. Now let's talk about matrices here. The magical grids that make machine learning a lot less chaotic. Think of them as spreadsheets on steroids. When you have got hundreds or even thousands of numbers to crunch, which is basically what machine learning is all about, matrices step in and say, don't worry, I got this. Now let's say you have a little expression like 4 cross 1 plus 2 cross 6 plus 5 cross 3. Sure, you could manually do multiplication and then add them all up. Or you could just use something way cooler, the dot product. Now let me explain what dot product is. A dot product is when two vectors, basically fancy 1D list of numbers, go on a speed date. Here's how it works. So let's first create these vectors. First element is 4, then 2, and then 5. I have taken this element from the product which we have mentioned above, 4, 2 and 5. And then next vector which we have is nothing but 1, 6 and 3. This is one dimensional. So we have our two vectors which are one dimensional each. So for doing dot product, I'll just place a dot here. So this will be my dot product. Now I want to perform dot product of these two. How it will happen? You simply take the first element from vector 1 and then multiply it with the first element of vector 2. So what it will be? 4 cross 1. Do the same for second pair. That is nothing but 2 cross 6 and then 5 cross 3. Then add up all those mini results into one big number. So I'm adding it up. What will be the result? If I multiply this, I'll get 4 plus 12 plus 15. So this sums up to 31 and boom, you have got your result. This is nothing but a scalar. So when you do the dot product of two vectors, you get output result as a scalar. Scalar is nothing but a single value. For any single value, we call it a scalar. This is a scalar, this is a scalar, this is a scalar. So this is what a scalar is. So when you do the dot product between two vectors, what you are getting is scalar. But a little warning here. Here's the deal. You can only do a dot product when both vectors have same length. See, the length of this vector is 3. That is nothing but the number of its elements must be same. Then only you can multiply each of them, right? If one vector has 2 elements and other has 3, your calculations are gonna throw a tantrum and your code will crash. Now let's see a quick recap. So what are vectors? This one-dimensional matrices. Think of them as a list of numbers in a single line, like your grocery list, but made of maths. And matrices? Well, they are like an entire Excel sheets full of those lists, ready to multiply, transform and power your AI. We'll see this. So far, we have danced with the dot products and now it's time for real drama. Matrices with multiple rows and multiple columns. Yep, they are no longer cute little number list. They have evolved. They have entered the villain arc. Think of scalar as a lonely number just vibing by itself. A vector is a group chat of numbers all in one line chatting away. And a matrix? Oh, it's a whole spreadsheet full of drama and mischief, like your cousin's WhatsApp family group. Now let's say I have two matrices here. This is A and this is B. So this is what I have 2 rows and 2 columns in a matrix. Let me show you some terminology of a matrix. So this is how we define a matrix in this square brackets. So these are nothing but your rows and these are nothing but your columns. Okay. So here I have given 3 arrows. So this is row 1, row 2, row 3 and this is column 1, column 2, column 3 and column 4. So what will be the dimension of this matrix? Dimension is nothing but number of rows multiplied by number of columns. So this matrix is of dimension 3 cross 4. So this is nothing but dimensions of what? Of a matrix. So this is how you write dimensions of a matrix. Now here you can see I have taken one matrix as A. So the dimensions for this is 2 cross 2 because I have 2 rows and 2 columns. And dimension for B is nothing but 2 rows and 3 columns here. Okay. So matrix multiplication is not like a regular multiplication. It's more like a cooking show. Chefs in a cooking show can act as a row. Columns can act as a recipe. And when you fire them together in a frying pan, you get something yum, good food. That is nothing but your resultant matrix. Enough about the food. Let's come back to our matrix. Now here I have 2 cross 2 matrix. Here I have 2 cross 3 matrix. Now how the multiplication will happen for them? So we have here A, we have here B. Now how do we multiply? To get the first element, take row 1 of A and column 1 of B. And then you do the dot product between this row and this column. So let's do it. I have this as 3. So for first entry, what it will be? 3 and 4. This I am doing dot product with the column 1, that is nothing but 3 and 1. So this will be my first entry. Then my second entry, here this element will be what? Take again the first row with second column. We are solving for first row and second column. So for first row, it is what? 3 and 4. Okay. Take dot product with what? 4 and 2. Then we are solving for first row and third column. So take this first row and third column. So what is my first row? That is nothing but 3 and 4. And then my last third column, 5 and 3. Okay. So this will be my first 3 elements for first row and all the columns. Similarly, for second row, take second row and then multiply it with each column to get the result. So I'll be taking 1, 2, dot product here. Maybe this mentioning of dot is not needed, but still I'll keep it here so that we understand, okay, we are doing a dot product. So 1 and 2, I am doing what? Dot product with first column. Then second row, second column, third column. So this will be nothing but my multiplication of what? A and B matrix. Now let's do the dot product. We know. How do we do the dot product? Take first element from this vector and first element from this vector, 1D vectors, and multiply. So 3 cross 3 plus 4 cross 1. For this it will be 3 cross 4 plus 4 cross 2. For this it will be 3 cross 5 plus 4 cross 3. Now next, this will be 1 cross 3 plus 2 cross 1. This will be 1 cross 4 plus 2 cross 2. And here we'll get 1 cross 5 plus 2 cross 3. Now let's solve this to get a final resultant matrix. 9 plus 4, what it is? 13. Then 12 plus 8, what it is? 20. Then 15 plus 12, 27. Then 3 plus 2, 5. 4 plus 8, 12. And 5 plus 6, 11. So this is the multiplication of A cross B. So this is how you multiply a matrix. So it's like a matrix dance party and everyone gets a turn. So now what's the size of this new party matrix? So resultant matrix will be nothing but number of rows of first. So that is nothing but 2. Number of row of first matrix and number of columns from second matrix, that is nothing but 3. So here you can see the resultant which we got has the dimension of what? 2 cross 3. Let me tell C. So this is what the dimension of my new resultant matrix is. So remember this one law here. What? If I have one matrix with dimension say A cross B, and if I have another matrix with dimension say B cross C, then only I can get this dimension A cross C if and only if the number of columns in my first matrix is same as the number of rows in my second matrix with which I am multiplying. Then only we can get this matrix. If this both are different, it is not able to multiply. We can't multiply this matrices when we don't have such kind of dimensions. Now one more thing to remember here, that matrix multiplication is not commutative. Let's understand what it means. In regular math, you can say 2 cross 3 equals to 3 cross 2, correct? This is also 6, this is also 6. But for matrix multiplication, it is illegal. When you multiply A cross B, that will never be equal to B cross A. Always remember this. Let's see an example for this. Let's say I have two matrices here, A and B. Both are 2 cross 2 matrix. The dimensions of both the matrix I am taking here is 2 cross 2. You can take any other, but just remember this value. The number of columns should match the number of rows of a second matrix. You can take any other values also. Now let's do first A cross B. What will be my A cross B? Again, same. First row, first column for first element. So when I say 3 cross 2 plus 4 cross 6 here, okay, this will be my first element, and again first row, second column, so 3 cross 5 plus 4 cross 7 here. Similarly here I'll get 1 cross 2 plus 2 cross 6, and here I will get 1 cross 5 plus 2 cross 7. So this will become my A cross B, which will be nothing but equal to 6 plus 24, 30. Here I'll get 34. This will be nothing but 14, and this will be nothing but my 19. So this is what A cross B is. Now let's do the opposite. That is nothing but B cross A. Okay, so when I do opposite, I'll be taking first row from B and first column from A. So what it will be like? It will be 2 cross 3 plus 5 cross 1. Here it will be what? 2 cross 4 plus 5 cross 2. Now here again, what we are doing? 6 cross 3 plus 7 cross 1. 6 cross 4 plus 7 cross 2. When I calculate this, I'll get result as 11. This will become 18. This will become 25. This will become 38. Now when you compare the results of these two, you can see that my A cross B is not equal to B cross A. Hence this matrix multiplication is not commutative. That means you can't say A cross B will be equal to B cross A. So in the context of machine learning, the order in which to multiply matrices can be very confusing. But the most important part is just getting the dimensions to match. The non-commutative property of matrix multiplication is important to keep in mind, but you won't have to deal with it much. Also, always check dimensions before you swap partners in this number dance. Hence, in a nutshell, matrix multiplication is nothing but contracting the dimensions. For example, say you have some matrix, one is 4 cross 8. And then you have another matrix 8 cross 3. So these are my two matrices with dimension. Now I want to multiply them. First, see, is it possible? Yes, because the number of columns in first matrix is same as the number of rows in second. So it is possible. Then what is the final output? We get it as remove the common one and then multiply the number of rows with the number of columns of second matrix. So this is the dimension. So you can see this whole dimension is contracted into this dimension now. So the new dimension will have matrix 4 cross 3 after the multiplication. Now that you know how matrix dimensions work, there is one last step before you successfully learn all the linear algebra you need to create a neural network. That is nothing but transposition of a matrix. Matrix looking weird? Just flip it. Take your matrix and swap rows and columns. So let's see. So if I have some matrix, say A, which has a dimension as 2 cross 3, that means 2 rows and 3 columns. Then when I do transpose of matrix A, that is nothing but A transpose. This T stands for transpose. So what will be the dimensions of my A transpose? This will become 3 cross 2. That means I'll have 3 rows and 2 columns. So this is how a transform works. Just take the rows, take the columns and flip it. It's like turning a portrait picture into a landscape picture. So here you can see once which was rows has become a column here, and once which was column has become a row here. It's like new haircut, new me version of a matrix. Now why transpose matters? Remember that example where you had one matrix as dimension 2 cross 2 and another matrix with the dimension 3 cross 2. This matrix didn't work, right? This multiplication for this didn't work because it was violating our rule, which was what? This and this should be same. So now what if I do transpose of this matrix? Let me do transpose of this matrix. So when I take transpose of this matrix, row become column and column becomes row. And here I have 2 cross 2. Now it is satisfying our condition. Which condition? Where for matrix multiplication, the number of column from first matrix should be same as number of row for second. So now when I multiply them, I get the final matrix dimension as 2 cross 3. Correct? So then this multiplication became possible as soon as I did transpose for a certain matrix. Matrix miracle, right? Transposition lets you force compatibility. Just like sneaking into an exclusive club by just changing your jacket. So this matrix transposition also gives us great flexibility in matrix multiplication according to this law. Now, what is this law of transposition? It is nothing but if I take one transposed matrix and multiply it with another matrix, it is as good as the multiplication of both the matrix. Try it out yourself. Grab two matrices, multiply them, then transpose. Now try the reverse method. Math logic. We are through now. Now let's summarize what all we have learned in this lecture. First is what is scalars? It is just a single number. Then vectors, it's just a number line up. Matrix, full on number tables. Then comes dot product, which always gives us a scalar value. Then we have matrix multiplication, which gives us a new matrix which has dimensions contracted together. Then something as multiplication only works if inner dimensions of both the matrix you are trying to multiply matches. Then transposing is as good as flipping rows and columns. Then order matters in matrix multiplication. Don't get it twisted. So that's all. Congrats, you have officially graduated the Matrix Academy. You now understand matrix dimensions, multiplication, transposition, the core tools you need to build a neural network from scratch. Next up, we'll learn about derivatives. Buckle up, it's gonna get computational now. See you in next discussion. Till then, keep practicing even if you get lost. Thanks for watching.